Okay, we're looking at the solution to the group activity for, I think it was week 10 or week 9 or something. I don't know. And hopefully you can see it. I think I called it week 9, but moved it, and we're now in week 10. And I need to hit pause over here. So just a sec. There we go. All right. And so with this one, the idea, there's a couple of principles at work here. So first, I'm going to say we've got a 0.5. I'm going to ignore sig fig so I can get this done quickly. And it says it's at rest this height above the ground. It impacts the ground and bounces up. So I'm going to call this V1 for the velocity at stage 1 and V2. You could call them initial and final or however you want to do it. Let's see. Okay, 500 ground. Okay, so then in this case, oh, and its speed after impact is n, where n is your breakout room. So we know this one is some number. It's some number of it could be 1, 2, 3, 4, 5 or something like that meters per second. Got it. And now in this case, if it's released 5.1 meters above the ground, V1 should equal, let's see. Well, we could do 1/2 mass times V1 squared is equal to mgh, because I'm comparing the energy. This would be, I suppose I should do it this way. Mgh, this is the initial energy, is all potential. It's released from rest. And this other one is the final energy right before it hits. We're ignoring drag. So I could see from this, I see that V equals the square root of 2gh. Now, in this case, I could plug in these numbers, and I'm just going to do that really quick. I had a calculator. Oh, man. Where'd it go? Oh, geez. All right. Where is that calculator? Here's one. So that's 19.6 times 5.1. And then I'm going to square root that. And I got basically 10. So this is V1 is about 10.0 meters per second. Now, if you had the earlier class could have used this same relationship, except I think the earlier class, I gave you the height final. So for the earlier class, you'd actually be using this energy equation to figure out V2. All right. So in short, we know this number is 10 meters per second from an energy problem. And we know this one is n meters per second from the problem statement. Again, the earlier class, maybe I gave you the 10 and you had to figure out the n instead. Something like that. Next, I know the video is shot at 30 frames per second, and the ball is going to come in here. And then in between here, you could imagine the bottom of the ball is flattened out instead of being perfectly spherical because it's in contact. And this is where it gets tricky. We don't know exactly how long it's moving down before it comes to rest, and then how long it's moving upwards. You could say, well, it takes 4 frames. Couldn't it just be half the time going down and half the time going up? Well, maybe, except the velocities aren't the same. So maybe it takes a little bit more time going downwards than going up. So I don't know the time required to come to rest. So I can't just say the time to come to rest is 2 frames. I can't say it's 4 frames. It's the time to reverse direction is 4 out of 30, right? If the frame rate is 30 frames per second, 1 frame is 1/30th of a second. So that's what we know from this wording. And this is just like what we did in tracker in week whatever that was. 1 frame equals 1/30th of a second if you have 30 frames per second. So delta T is this amount of time. So now the force net on the object is a vector. That's equal to mass times velocity final minus mass times velocity initial, all divided by the change in time. If you're wondering where I got that equation from, it's from the impulse equation, delta P over delta T. Well, the upper part of that numerator is delta P. This junk up here, give me a sec, that junk is delta P. So what is V final and V initial? V final is positive n because it's going upwards. V initial is negative 10 because it's going down. You could think about that being in the J hat. I'm being sloppy with units. Okay, yes, I should have meters per second on those. I'm a bad person. The mass, as we said, is 0.5 kilograms. This gets you the net force. Now, after all of that, you got the net force. How do you do this? Well, net force is m times acceleration. When the ball hits the ground, it's actually got a normal force up in the J hat minus mg down in the J hat. So how do you get the normal force? This part right here is what you get from delta P over delta T. If you recall, this is what I said back in that lecture. I said, look, MA is one way of getting force, but this way is a better way of getting force. This way is accurate even when we're doing relativity. So this gives you the the right side of the equation. Mg, that's pretty easy. All the J hats cancel out. So basically you get N equals Mg plus the magnitude of delta P over delta T. And it's pretty quick. Some of you might say, do I have to use work and energy to get this velocity? Could I have just used kinematics? You could have. But I liked this problem because you had to think about practical real life issues that would show up if you're doing video capture analysis. You have to think about momentum and time because we don't know the exact time to come to rest. And so you could use basically 3 of the 4 major tools that we had. We have 4 major tools, right? We have F equals ma, or just forces. We have kinematics, we have energy, and we have momentum. And so you had to use 3 of the 4 tools to solve this problem. Actually, we have some new ones based on today's lectures. Now we're going to have torque, which is very similar to forces. We also have rotational kinematics. So we're starting to increase our toolbox. That's the first one. Anyone that's here have questions on that?
Quick question.
Yes.
All right. So the part I got stopped on was like the m acceleration equals to delta P over delta T. So m acceleration equals delta P over delta T.
Yeah. So should we go over that one more time just to make sure? The force net on an object, by definition, is equal to ma. That you're okay with, right?
Yes.
However, what I'm telling you is another way of writing that is change in momentum over change in time. That's another way to get that. And this one works great because we know V at stage 1 and we know V at stage 2 as vectors. So it turns out we don't know right? When this ball is smushing and stuff, it's hard to do kinematics while it's smushing to get the acceleration because we don't know exactly how many frames it takes to stop. So what I'm saying is you could use the velocity information in the mass to get delta P. And we could use delta T from the frame rate. And that is equivalent to what we would get if we could somehow figure out the kinematics while the ball is actually moving down. If you watch this thing, let's say here's the first frame where it touches the ground. So this is 1. And then it starts to smush a little bit, right? 2, 3, And then maybe it starts to re-expand. 4. The idea is for these 4 frames, it's very difficult. Whoops, 3 comes after 2. For those 4 frames, it's very difficult for us to say, well, how far did it move? Because we're talking about the center mass of this thing. I don't know where the center mass is when it starts getting smushed. So it's not obvious how far it moves in what amount of time if we're looking at the frame rate. So it's very difficult to use these to get the acceleration directly. Is that good on your question, Jesse?
Yep, that was the only part I was missing for the answer. So,
all right. So there's that. Okay. Sneaky. If you want, this is, remember that problem I mentioned, Chris Moon, that has 3 O's? That was workbook problem. If you want to see this again, another way with all the solution details worked out, let me tell you what workbook problem. Problem 9.48. So this is nearly identical to workbook problem 9.48. Now, if you look at, you might be saying, well, dude, how come we didn't worry about mg in workbook problem 9.1? In 9.1, it's a little bit different because the ball was moving horizontally and we ignored mg because the collision time was so short. In this one, because the ball's going vertically, we ignore the mg to get the net force. But yeah, it's a little bit more like that. All right. Is that good on that one? I think so.
Yeah.
And then should we look at the other one just in case? The other one I hope was easy.
Yeah, it was just like the problems in the workbook.
Yeah, and so here the idea is depending on whether I said right or left end, this one says the right end. So this is n over 9. And so that means this entire distance is L. So then the trick is here, this limit is not negative L, not negative L over 2. It looks like this would be, the answer would be negative times the quantity L minus n over 9.
Sweet.
Which I guess you could rewrite that as n over 9 minus L. However, that's usually a bad form just because it's not obvious the answer is negative. Whereas here you're saying, look, I know n over 9 is, so this clearly shows you the answer should be a negative number. Either one would be full credit, like I said. And then it's just the integral of x dm over the integral of dm. And then in this case, dm is just that lambda times dx, where again, lambda is that whole function with the cosine in there or something like that. Okay. Was it cosine or was it cosine squared? Oh, it's just cosine, I think, right? All right. And so that's that solution. I'm going to stop there and I'll share that with everybody later. Let's end the live stream on that, unless there was a question on that. Was that pretty good?